Hello, this is Mrs. Pullen, and this is our second unit on finding zeros of a function and our first lesson on radicals and conjugates. And I am breaking this lesson into 3 separate videos. For the first video, we're going to be simplifying radicals. In order to simplify a radical, we're going to take the radicand and break it into 2 factors. One factor is going to have the highest perfect square, and the other factor is going to be the non-perfect square. So in order to do this, you really need to know your perfect square. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so forth. You really need to memorize these. And we're just going to go down the list. So let's go through some examples of this. If I want to break up square root of 12, we know the highest perfect square in 12 is 4. I'm going to just make this a little less big. So square root of 4 is the highest perfect square, and this is the non-perfect square. So the square root of 4 is 2, and square root of 3 I can't simplify further, so this is my final answer. We can do the same process for the second one. 72, the highest perfect square, is 36. If you were unsure, what you could do is first start dividing 72 by 2, and you would get 36 right away. Square root of 36 is the perfect square. This is the non-perfect square. I can simplify this into 3 times 6 rad 2, and now I can multiply those coefficients together. I'd like you to put the video on pause and try number 3 on your own. Okay, you're now pressing play at this point, and you should have broken square root of 50 to square root of 25 and 2, 18 to square root of 9 and square root of 2, and 8 into square root of 4 times square root of 2. This simplifies into 5 rad 2 minus 3 rad 2 plus 2 rad 2, and now I can combine these radicals since they have the same radicand and they both have this, all of them have the same index. Example 4, we're actually going to be performing an operation. We're going to be distributing square root of 2x to both of those terms. So this becomes square root of 2x times square root of 3x minus square root of 2x times square root of 2x. When we multiply radicals, we'll multiply the radicands and multiply the coefficients on the outside. There's nothing on the outside of these. We don't have to worry about that. This becomes 6x squared minus, and the second one we're going to do the same process, and we get 2 times 2 is 4, and x times x is x squared. We now can simplify. This simplifies into square root of x squared, that's our perfect square piece, times square root of 6. This simplifies, the whole thing is perfect square, so we don't have to worry about that, simplifying that. This becomes x square root of 6 minus 2x. And we're just going to reorder this because we normally put the radical piece second. So this becomes negative 2x plus x rad 6. For number 5, instead of a monomial times a binomial, we have two binomials, so you can either use the box method or you can use double distribution or FOIL. So square root of 3 times square root of 3, that's our first times first. Our outer is square root of 3 times square root of 2. Our inner is minus square root of 2 times square root of 3. And last times last is minus rad 2 times rad 2. This becomes square root of 9 plus square root of 6 minus square root of 6 minus square root of 4. The inner and the outer cancel, and we're left with 3 minus 2 when we simplify square root of 9 and square root of 4. And so our final answer is simply 1. Notice that the only difference between these two binomials is the middle sign. This is known as a conjugate pair. For the last problem, number 6, I'd like you to put the video on pause a second and try the problem on your own. Notice how I separated out this term squared. So now I have two binomials and I FOILed it. Notice I could have said square root of 3 times square root of 3 was 3 right away. So you could skip that step when you're multiplying like radicals. Notice that in this case, since they're not conjugate pairs, that you can't cancel those middle terms and you actually have to combine them. Let's go on to the next page, next slide. For number 7, we're now going to simplify radicals with variables. Variables with an even exponent are perfect square. To take the square root, we're going to divide the exponent by 2. So x to the 10th is a perfect square because 10 is a even number. So to take the square root, we're just going to divide the exponent by the index of 2. So this simply is x to the 5th. For problem number 8, 9 may be a perfect square, but x to the 9th is not. So we need to break it down into the highest perfect square and the non-perfect square. So the highest even number closest to 9 without going over is x to the 8th. And to make it whole, we're going to multiply it by x to the 1st, or just x. X to the 8th is a perfect square, so we're going to just divide the exponent by 2. And my final answer is x to the 4th times square root of x. So now we have both number and a variable. So to break it up, we're going to break it into the perfect square piece and the non-perfect square piece. The highest perfect square in 50 is 25, and 2 is the non-perfect square factor. And the highest perfect square in x to the 6 is x to the 6 times x. This simplifies into 5x, divide the exponent by 2, and here's my final answer. And the last one in this section, again, same philosophy. We're going to break it into the perfect square and the non-perfect square piece. Highest perfect square in 48 is 16. To make it whole, we're multiplying it by 3. And now it's a to the 10th and b squared. This simplifies to 4a to the 5th b times square root of 3.